Thank you. Right, so that's going to be a tough act to follow, but I'll try my best. So this is joint work with my colleague Helen Liu from the University of Auckland. And what we're trying to do here is asking ourselves, how can we get some intuition into what the machine is actually doing? So this builds onto the field of explainable AI. And our contribution here, so what I'm going to do here, clever thing, is summarize my talk so that you all know what it is when I run out of time. In a nutshell, gradient boosting machines, it's a kind of tree-based method. Essentially, what you do is you train the first tree and then you train the subsequent trees on the residuals of your ensemble of trees. And what we do is we show that there is a way to decompose any GBM prediction into the training instances. Right? So let me show you what that looks like. So, of course, if you have something like this, you need to give it a name. I've settled on axle weights, so there's the original axle weights and then there's my axle weights. They're not the same thing. And this builds on previous work with my co-author, where we actually applied some of this in a practical setting, valuing companies directly from accounting data. But the focus here is more on the algorithm and what can you do with it. Okay, so to set the scene, you've all seen a data matrix like that. It really has two dimensions, if you like. There's the features, right? And then there's the instances. Now, the bulk of the work that we see in explainable AI tends to focus on the role of the features. And so, some of the very common approaches there are LIME and SHAP. What we do is, instead of focusing on the features, which there are approaches for that already, we try to explain model predictions in terms of the instances that were influential in driving that prediction rather than the features. Right? So it's not a substitute for feature importance. Think of it as being complementary. Okay, so I'll skip over all the formal stuff and also the algorithms. Trust me, it's just a bunch of linear algebra. Right. So let's get to something a little bit more interesting. I thought, let's do a little application, and the one that I hit on is smoking prevalence by country, right? So there's this beautiful data set from the World Bank called the World Development Indicators, and I train a very simple GBM to predict smoking prevalence by country. So you can see that there's a reasonable fit there. So the question is, now that we have this model, what can we get out of it? Now, conventionally, you'd go to something like SHAP values, and that's what we have here. And you can see that, firstly, the feature space here is large. We have about 700 features, right? And so it tells you that the probability of deaths is, for age 20 to 24, is very influential. Now, the causality could go both ways, but I think you really have to smoke a lot to kill yourself at age 22. So I think perhaps it's the other way around. If there's a good chance that you're going to die early, perhaps you don't need to worry about smoking. But of course, association is not causality, so we need to be careful. This is the other way of looking at it. And what this is basically doing is it's saying for, say, Nigeria over here, these are the instances that most contributed to the prediction for Nigeria. And what this basically tells you is that these are countries that are, in a sense, similar. And the nice things about these weights is you get one vector of weights for each prediction, but when you put them together, you get a matrix. And that means, so how do you use them? You take the weights, you multiply it by the training data, and that gives you the prediction. And that actually works, so there's a little, see that number? And that number, it's the same. It will work for every prediction, and we show that that's the case. The other cute thing is, once you have this matrix, you can use it as a dissimilarity matrix, which means you can get clustering out of it, right? Hierarchical agglomerative clustering. And this tells you, in a kind of neat way how things fit together, and also what's kind of the off-diagonal links. I think that's useful. The other thing that you can do with it is you have a symmetric matrix, right? It can be an adjacency matrix. That gives you a network or a graph. Now, what I've done here is I've sorted everything from high to low. So Nigeria has a very low smoking rate, whilst Myanmar has a very high one. And what these links tell you is that there are clusters, countries that kind of belong together based on smoking preference. So there's a cluster here. And you also have links that are not immediately obvious between, say, for instance, Congo, where smoking preference is low, and Thailand, where it's high. And that, in a nutshell, is what I have to say. And that's it. Thank you very much.